Welcome to today's problem-solving session. We'll be exploring an interesting problem from LeetCode, titled Car Fleet. This problem requires us to think critically about the movement of cars on a highway and how they form fleets. Let's dive in and break it down step by step. In this problem, we are tasked with determining how many car fleets will arrive at a destination. Each car starts at a unique position along a one-dimensional road and moves at a constant speed. A car fleet is defined as a group of cars that travel together to the destination without any car in the fleet being passed by another. Essentially, if one car catches up to another and they travel together at the same speed, they form a fleet. The inputs to the problem include the target, which is the position of the destination, a list of starting positions for the cars, and a list of their respective speeds. The output is a single integer representing the total number of car fleets that reach the destination. For example, given the input where the target is 12, the car positions are 10, 8, 0, 5, 3, and their speeds are 2, 4, 1, 1, 3, we need to calculate how many fleets form as they travel to the destination. The output for this example is 3 fleets. First, we sort the cars by their starting positions in descending order. This gives us the positions as 10, 8, 5, 3, 0, and their corresponding speeds as 2, 4, 1, 3, 1. Next, we calculate the time each car takes to reach the destination. For the car at position 10, it takes open parenthesis 12 minus 10 close parenthesis divided by 2, which is 1 hours. The car at position 8 also takes open parenthesis 12 minus 8 close parenthesis divided by 4, which is 1 hours. The car at position 5 takes open parenthesis 12 minus 5 close parenthesis divided by 1, or 7.0 hours, while the car at position 3 takes open parenthesis 12 minus 3 close parenthesis divided by 3, or 3.0 hours. Finally, the car at position 0 takes open parenthesis 12 minus 0 close parenthesis divided by 1, or 12.0 hours. Based on these times, we can see that the cars at positions 10 and 8 arrive at the same time, so they form one fleet. The car at position 5 takes 7.0 hours to reach the destination, which is much longer than the fleet of cars at positions 10 and 8. This means the car at position 5 forms its own fleet. The car at position 3 takes 3.0 hours, which is less time than the car at position 5, but it cannot catch up to the fleet ahead of it, so it also forms its own fleet. Finally, the car at position 0 takes 12.0 hours to reach the destination, which is longer than any of the other cars, so it forms its own fleet as well. In total, we have 3 fleets. In contrast, if there is only one car, such as in the second example where the target is 10, the position is 3, and the speed is 3, that single car forms its own fleet, and the output is 1. In the third example, the target is 100, the positions are 0, 2, 4, and the speeds are 4, 2, 1. Here, we first sort the cars by their starting positions in descending order, giving us positions 4, 2, 0. The corresponding speeds are 1, 2, 4. Now, we calculate the time for each car to reach the destination. The car at position 4 takes open parenthesis 100 minus 4 close parenthesis divided by 1, which equals 96.0 hours. The car at position 2 takes open parenthesis 100 minus 2 close parenthesis divided by 2, or 49.0 hours. Lastly, the car at position 0 takes open parenthesis 100 minus 0 close parenthesis divided by 4, or 25.0 hours. Since the fastest car starts at position 0, it catches up to both cars ahead of it, forming a single fleet. As a result, the output is one fleet. The key observation here is that faster cars starting behind slower cars can catch up to them, and this may result in them forming a single fleet. Additionally, the constraints of the problem ensure that the input size and values can be large, so our solution must be efficient. The number of cars, n, can be as large as 100,000, and the target position, car positions, and speeds can also be very large. All positions are distinct, and every car has a positive speed. These constraints require us to use an approach that avoids excessive computation or memory usage, ensuring that the solution scales well even for the largest inputs allowed by the problem. There are several edge cases to consider. First, if there is only one car, it will always form its own fleet. Second, when cars are already sorted by their positions and their times to reach the destination do not overlap, each car forms its own fleet. Third, when faster cars start behind slower cars and catch up to them, they form a fleet together. Finally, we must handle edge cases involving the maximum constraints, such as very large values for n, target, position, and speed. It is important to ensure that the solution remains efficient in terms of both time and space complexity to handle these extreme scenarios without exceeding computational limits. To begin, let's consider the brute force approach. The intuition here is to simulate the movement of all the cars, checking if and when one car catches up with another to form a fleet. For each car, we calculate its arrival time at the destination, and then repeatedly compare positions and speeds to determine how cars group together into fleets. While this method is straightforward and easy to understand, it becomes inefficient when the number of cars, denoted as n, is large. The key observations are that cars closer to the destination will either reach first or be caught by faster cars behind them, and once two cars merge into a fleet, they travel together at the same speed. However, because this approach involves repeated comparisons between every pair of cars, the time complexity is quadratic, or O(n squared). This makes it impractical for larger inputs, despite its simplicity. The space complexity, on the other hand, is linear, or O(n), as we need to store the arrival times of the cars. Now, let's look at the optimized approach. Here, instead of simulating the movement of cars, we directly calculate the arrival time for each car using the formula time equals target position / speed. By sorting the cars based on their starting positions, from farthest to closest to the destination, we can process them in reverse order. This allows us to consider each car's influence on the cars behind it. As we iterate through the sorted list, we compare each car's arrival time with the arrival time of the last fleet. If the car's time is greater, it cannot catch up to the fleet ahead and forms a new fleet. If its time is less than or equal to the last fleet's time, it merges into that fleet. The key insight here is that sorting by position ensures we process cars in a logical order, avoiding unnecessary simulations. This reduces the problem to a simple sequence of comparisons. The time complexity is O(n log n), dominated by the sorting step, while the space complexity remains O(n), as we store positions, speeds, and arrival times. This makes the approach much more efficient for large inputs. Given the trade-offs, we select the optimized approach as our strategy because it strikes a balance between simplicity and efficiency. By focusing on arrival times and sorting the positions of the cars, we eliminate the need for complex simulations and repetitive checks. This method scales well to larger inputs, such as when n is in the range of tens of thousands, and avoids the inefficiencies of the brute force approach. Comparing the two, the brute force method is conceptually easier but suffers from quadratic time complexity, making it unsuitable for larger datasets. The optimized method, while slightly more involved, leverages sorting to reduce the time complexity to O(n log n), making it far more practical. The key realization, or aha moment, was understanding that sorting the cars by position allows us to process them in reverse order of influence, simplifying the problem to a series of arrival time comparisons. This insight not only simplifies the logic but also ensures the solution is both robust and scalable. To solve the car fleet problem, we first need to understand the goal. We have a group of cars traveling on a one-dimensional road, each starting at a specific position and moving at a certain speed. The task is to determine how many distinct car fleets will reach a given destination. A car fleet is a collection of cars that travel together at the same speed, where no car overtakes another within the fleet. This means that once a faster car catches up to a slower one, they move as a single unit at the slower car's pace. The input for the problem includes two arrays: position, which tells us the starting position of each car, and speed, which gives the speed of each car. We also have a target, which represents the destination. The output is a single integer representing the number of car fleets. To solve the problem, we start by pre-processing the data. First, we pair each car's position with its speed to create tuples, making it easier to process them together. We then sort these tuples in descending order of position, so we analyze cars in the order they are closest to the destination. This step is critical for determining how fleets form as the cars approach the target. Once the cars are sorted, we calculate the time it takes for each car to reach the destination. For any car starting at a given position, this arrival time is computed using the formula target position I/speed I. This tells us how long it will take each car to cover the remaining distance to the target. As we iterate through the sorted list, we store these arrival times. Now, to simulate how fleets form, we initialize two variables, fleets to count the total number of fleets, and current_max_time to track the slowest arrival time in the current fleet. For each car in the sorted list, if its arrival time is greater than the current_max_time, it indicates that the car cannot catch up to any existing fleet and forms a new fleet. In this case, we increment the fleet's counter and update current_max_time to the arrival time of this car. Otherwise, if the car's arrival time is less than or equal to current_max_time, it simply joins the existing fleet, as it will eventually catch up to the cars already in that group. After processing all the cars, the value of fleets gives us the total number of car fleets that will reach the target. The key insights that make this approach efficient include sorting the cars by their starting positions in descending order. This ensures we process them in the order they approach the destination, from closest to farthest. Fleet formation is based solely on arrival times. If a car's arrival time is less than or equal to the slowest car in the current fleet, it cannot form a new fleet. This simple comparison allows us to group cars without requiring additional data structures, keeping the implementation clean. After sorting, the algorithm processes the cars in a linear pass, making it very efficient. The time complexity is O(n) log n due to the sorting step, and the subsequent iteration through the cars is O(n), resulting in an overall complexity of O(n) log n. The space complexity is O(n) for storing the list of car tuples. Additionally, we must consider edge cases. For example, if all cars have the same speed, each one forms its own fleet unless their positions overlap. If all cars start at the same position, they form a single fleet since they all move together. Similarly, if multiple cars have the same arrival time, they naturally form a single fleet. Finally, if the input is empty, meaning there are no cars, the expected output is simply 0 fleets. Here's a concise Python implementation of the solution. We start by pairing positions and speeds into tuples and sorting them in descending order of position. We then initialize two variables, fleets to count the number of fleets and current_max_time to keep track of the slowest arrival time in the current fleet. For each car in the sorted list, we compute its arrival time using the formula, target p/s, where p is the car's position and s is its speed. If the car's arrival time exceeds current_max_time, it forms a new fleet, so we increment the fleet's counter and update current_max_time to this car's arrival time. Otherwise, the car joins the existing fleet. Finally, we return the total fleet count. The time complexity of the algorithm is O(n) log n due to sorting, and the space complexity is O(n) for storing the sorted list. This implementation is efficient and handles all edge cases, providing a robust solution to the car fleet problem. This solution uses a greedy algorithm to calculate the number of car fleets arriving at the target. First, we pair the cars' positions and speeds, then sort them in descending order of their starting positions. This ensures we consider cars closest to the target first. We iterate through the sorted list, calculating the time required for each car to reach the target. If the calculated time is greater than the time of the current fleet, a new fleet is formed. This is because no car ahead will slow down to merge with the current one. We increment the fleet count and update the maximum time to reach the target. Finally, the total fleet count is returned as the result. This solution is efficient with a time complexity of O(n) log n due to sorting, where n is the number of cars. In this implementation, we start by importing necessary packages and defining the solution class with the carFleet method. The input parameters include the target distance, an array of positions, and an array of speeds. The first step is to pair positions with their corresponding speeds and store them in a 2D array named cars. Each subarray represents a car, where the first element is its position and the second is its speed. Next, we sort this cars array in descending order based on the position, ensuring that we process the cars starting from the ones closest to the destination. This is achieved using the arrays.sort method with a custom comparator. Once sorted, two variables are initialized, fleets, which will track the total number of car fleets, and time to reach, which keeps track of the time it takes for the last fleet to reach the destination. We then iterate over the sorted array to calculate the time each car takes to reach the target. This is done using the formula target cars I0 / cars I1, which divides the remaining distance by the car's speed. If the calculated time for the current car is greater than the time to reach of the last fleet, it means this car cannot catch up to the previous fleet and forms a new fleet. In that case, we increment the fleet's counter and update the time to reach variable to the current car's time. Finally, after processing all the cars, we return the total number of fleets as the result. This value represents how many distinct groups of cars will reach the target without merging along the way. The implementation ensures that each car is considered in descending order of position, which simplifies the logic of determining whether a car can catch up to a fleet ahead of it. The solution is efficient, leveraging sorting and a single traversal of the car's array, making the time complexity O, n log n, due to the sorting step. In this example, we have a target of 12, with cars positioned at 10, 8, 0, 5, and 3, and their respective speeds are 2, 4, 1, 1, and 3. The first step is to pair each car's position with its speed and sort them by position in descending order. This gives us the list of cars as 10, 2, 8, 4, 5, 1, 3, 3, 0, 1. Sorting by position ensures we process cars starting from the one closest to the target, working backward. Next, we initialize two variables, fleets, which starts at 0 to count the number of car fleets, and time_to_reach, set to 0 to track the time it takes for the last fleet to reach the target. These variables will help us determine when new fleets are formed and when cars join existing ones. Now, we process each car in descending order of position. First, the car at position 10 with speed 2 takes open parenthesis 12 minus 10 close parenthesis divided by 2 is equal to 1.0 hours to reach the target. Since this time is greater than the current time_to_reach of 0, this car forms a new fleet. We update fleets to 1 and time_to_reach to 1.0. Next is the car at position 8 with speed 4, which takes open parenthesis 12 minus 8 close parenthesis divided by 4 is equal to 1.0 hours. This time is equal to the current time_to_reach, so this car joins the existing fleet. Moving on, the car at position 5 with speed 1 requires open parenthesis 12 minus 5 close parenthesis divided by 1 is equal to 7.0 hours. Since this time is greater than the current time_to_reach of 1.0, it starts a new fleet. We update fleets to 2 and time_to_reach to 7.0. The car at position 3 with speed 3 takes open parenthesis 12 minus 3 close parenthesis divided by 3 is equal to 3.0 hours. This time is less than or equal to the current time_to_reach, so it joins the existing fleet. Finally, the car at position 0 with speed 1 takes open parenthesis 12 minus 0 close parenthesis divided by 1 is equal to 12.0 hours, which is greater than the current time_to_reach of 7.0. This car forms a new fleet, bringing fleets to 3, and time_to_reach is updated to 12.0. After processing all cars, we determine that the total number of fleets is 3. Moving to another example, here the target is 10, with positions 6, 8, and speeds 3, 2. First, we pair the cars and sort them by position, resulting in 8, 2, 6, 3. We initialize fleets to 0 and time_to_reach to 0. Starting with the car at position 8 with speed 2, it takes open parenthesis 10 minus 8 close parenthesis divided by 2 is equal to 1.0 hours to reach the target. Since this time is greater than time_to_reach, this car starts a new fleet. We update fleets to 1 and time_to_reach to 1.0. Next, the car at position 6 with speed 3 requires open parenthesis 10 minus 6 close parenthesis divided by 3 is equal to 1.33 hours. This time is greater than the current time_to_reach, so it does not start a new fleet and joins the existing one. As a result, the total number of fleets remains 1. In the final example, we have a target of 15, but there are no cars. Since the position and speed arrays are empty, pairing them results in an empty list of cars. With no cars to process, the number of fleets remains 0. This demonstrates that when there are no cars, the output is simply 0 fleets. These examples show how we calculate fleets in various scenarios, including standard cases, cars already in one fleet, and the absence of cars. The time complexity of this solution is driven by two main operations. First, we sort the cars by their positions in descending order. Sorting here is performed using Python's sorted function, which has a time complexity of O n log n for a list of n elements. This means that the sorting step is the most computationally expensive part of the solution. Next, after sorting, we iterate through the cars exactly once to determine the number of fleets. Each iteration involves straightforward operations, like calculating the time for a car to reach the target and comparing it to the current fleet's time to reach. These operations are O(1) each, and since there are n cars, this step contributes O(n) to the time complexity. When we combine these two steps, the dominant term is O(n log n) from sorting, so the overall time complexity of the solution is O(n log n). Now let's look at the space complexity. This includes both the space used for computations and any auxiliary space required. When sorting, the sorted function creates a new list to store the tuples of position and speed, requiring O(n) space since there are n cars. Additionally, Python's timsort algorithm, used in sorted, may use up to O(n) auxiliary space in the worst case. Beyond sorting, the algorithm uses some space for variables such as fleets and time_to_reach, but these are constant space, or O(1). The sorted list of cars, which contains n elements, also requires O(n) space. Combining these factors, the dominant space usage comes from the sorting operation, making the total space complexity O(n). When comparing this solution to a naive approach, the benefits of our optimized method become clear. A naive solution might simulate the movement of all cars step by step, checking for collisions at each time step. This would involve repeatedly comparing every pair of cars, leading to a time complexity of O(n squared, or worse, depending on the number of cars and time steps. In contrast, the current solution uses a much more efficient strategy. By sorting the cars and leveraging a single pass to determine fleets, we reduce the time complexity to O(n log n, and the space complexity to O(n). This avoids the inefficiencies of explicit simulation and instead uses mathematical reasoning to group cars into fleets quickly and effectively. Now, let's discuss how the solution performs in different cases. In the best case, the cars are already sorted in descending order of position. However, even in this scenario, the sorting step still takes O(n log n, so the total time complexity remains O(n log n). For the average case, where the cars are in a random order, the sorting step continues to dominate, resulting in the same O(n log n) complexity. Finally, in the worst case, the cars are sorted in ascending order of position, which requires the maximum number of comparisons during the sorting process. Still, thanks to the efficiency of timsort, the sorting step remains O(n log n, and the overall complexity does not change. Thus, regardless of the input arrangement, the time complexity consistently stays at O(n log n. To solidify our understanding, let's break down the mathematical reasoning behind the big O complexity. Sorting the cars list involves dividing it into smaller sublists, which requires log n levels of division. At each level, comparing and merging the elements involves O(n) work. This gives the sorting step a time complexity of O(n log n. After sorting, iterating through the cars to determine fleets involves a single traversal, which requires O(n) operations. Adding these together, the total time complexity becomes O(n log n plus O(n), which simplifies to O(n log n, since the sorting step dominates. For space complexity, the most significant factor is the sorted list and auxiliary data structures, which require O(n). No additional significant space is used, so the total space complexity is O(n). When solving the car fleet problem, there are some common mistakes you should be aware of. First, incorrect arrival time calculations can throw off your entire solution. The arrival time for each car is calculated as the distance to the target divided by its speed, or target position/speed. If you forget to account for this or miscalculate it, the fleets won't form correctly. Another mistake is grouping fleets prematurely. Without sorting the cars by their starting positions, it's easy to group them incorrectly because you won't process overtakes in the right order. Sorting by position, from farthest to closest to the destination, ensures your logic aligns with how cars actually interact on the road. Lastly, avoid a brute force approach, like simulating step-by-step movements for all cars. This can result in a time complexity of n squared, or worse, which is highly inefficient, especially for larger inputs where n can be as large as 10,000. Instead, we aim for more scalable solutions. Now, let's talk about two other pitfalls to watch for. Overlooking edge cases can lead to subtle bugs in your solution. For example, think about scenarios where all cars start at the same position or move at the same speed. These can affect how fleets are grouped, and if not handled properly, you might miss some fleets entirely. Another potential issue is floating point precision errors, which can occur when comparing arrival times. Directly comparing floating point numbers can lead to unexpected results, especially in languages like Python or Java, due to how numbers are represented in memory. To avoid this, consider using a small tolerance for comparisons or work with integers if possible. Addressing these issues ensures your solution is robust and handles all edge cases effectively. To approach car fleet problems effectively, there are a few key insights to keep in mind. Sorting is often a critical first step. It ensures you process the cars in the correct order, starting from the farthest position. Once sorted, a greedy strategy works best. By iterating through the cars in reverse order and maintaining a stack to track fleet arrival times, you can efficiently determine when cars merge into fleets. It's important to understand the trade-offs here. The greedy approach is optimal because it avoids unnecessary computations, achieving n log n time complexity due to sorting, followed by a single linear pass. Brute force, by contrast, would be far less efficient. During interviews, be prepared to explain why this approach works, emphasizing its efficiency. Also, edge case awareness, such as handling identical speeds or positions, can help you stand out. Lastly, note that this problem shares similarities with other greedy problems, like queue reconstruction by height or minimum number of arrows to burst balloons, so practicing these can deepen your understanding. Finally, let's look at some alternative approaches to solving car fleet problems. The brute force simulation method involves moving all cars step by step and checking if one car catches another. While this is simple to implement, it's highly inefficient with a time complexity of n squared, or worse, making it impractical for larger inputs. A better alternative is the greedy approach with sorting, which we discussed earlier. By sorting cars by position, iterating in reverse, and using a stack to manage fleets, you achieve an optimal balance of simplicity and performance with n log n complexity. Another approach involves using a priority queue or heap to dynamically merge fleets based on their arrival times. However, this adds implementation complexity and is generally less efficient than the greedy method. While it's good to know these alternatives, the greedy approach remains the most intuitive and scalable solution for this problem. Great job! We've successfully tackled the car fleet problem. Remember, sorting and stack-based approaches are powerful tools in problems like these. Thanks for joining me today, and don't forget to practice similar problems to strengthen your skills. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!